Okay, let's dive right into a truly ambitious idea. Imagine just for a second that all the fundamental pieces of the universe, gravity, the forces like electromagnetism, the nuclear forces, all the tiny particles making up you and me,
Uh-huh.
what if they didn't start as separate things you just had to list out?
Like ingredients you just throw in a pot.
Exactly. What if they all emerged completely naturally from just one single elegant geometric structure?
That's a really compelling thought. Suggests, well, a much deeper unity in nature than maybe our current theories show. Where sometimes it feels like we're bolting different parts together.
Right. And that's precisely what we're unpacking today. We're taking a deep dive into Dr. Eric Weinstein's proposed theory of everything, which he calls geometric unity.
And our source material for this is a pretty detailed presentation that lays out the theory's ideas.
Yeah, it's detailed. And we should say up front, some of it gets mathematically quite involved.
It definitely does.
Yeah.
Geometric unity uses some sophisticated math. But our goal here isn't to make everyone a differential geometer. It's more about cutting through that complexity.
Finding the essential core ideas.
Exactly. Finding those key aha moments, the surprising insights, and presenting them in a way that's, well, approachable for you listening, someone who gets science and engineering, but maybe doesn't live and breathe theoretical physics or abstract math every day.
Think of it like this. We're trying to find the shortcut to understanding the big picture of geometric unity, like grasping how a building stands by understanding its foundations and main supports without calculating the stress on every single bolt.
We're finding that essential structure.
Yeah.
Because the dream of any theory of everything is really about elegant simplicity, isn't it?
Start with minimal assumptions.
And see if the known universe just sort of pops out. That's the big goal for geometric unity.
Okay, so before we get into the weeds of G itself, maybe we should quickly clarify what physicists even mean by a theory of everything. It's not just quantum gravity, is it?
Oh, much more. Quantum gravity is specifically about squaring gravity with the quantum world. A theory of everything, or TOE, aims much higher.
It needs to bring everything under one roof.
Pretty much. It's aiming for a single framework that covers both general relativity, Einstein's theory of gravity, and spacetime.
And the standard model of particle physics.
Right, which describes all the known fundamental particles and the forces between them, except gravity. So TOE wants to unify everything we currently understand at that fundamental level into one coherent story.
Okay, unification. That's the name of the game. So where does geometric unity propose to start building this grand structure?
It actually starts somewhere quite simple, almost deceptively so, just a bare four-dimensional space. Let's call it X4.
It's 4. But it's not space-time yet. No clocks, no rulers built in.
Not yet. No inherent way to measure distance or time intervals. No curvature defined from the start. It's just a 4D canvas.
And here's where GU takes a really different path, isn't it? Usually in physics, you'd, pick a metric for your space-time, assign a way to measure distances.
That's the standard approach. But GU does something quite radical. Instead of choosing one specific metric for this X4 space,
it considers all of them.
Exactly. It considers the space of all possible ways you could measure distances on X4, point by point, all at the same time.
Wow. Okay, so instead of one ruler, you have the set of all possible rulers at every single point.
That's a good way to picture it. And this collection of all possible metrics at each point creates a much larger space. It turns out to be 14-dimensional.
14 dimensions? That's quite a jump from 4.
It is. Dr. Weinstein calls this the observer space, or Y14.
Y14, the observer space. That sounds pretty central. And what's the big payoff for doing this, for considering all metrics simultaneously?
This is where GU tries to tackle a really deep, long-standing problem in fundamental physics. It's about matter particles, fermions, like electrons and quarks.
Okay.
These particles are described mathematically by objects called spinors. Now, traditionally, the definition of a spinor seems to depend on having a specific metric, a specific geometry on spacetime.
Right, you need the geometry to define the spinor.
But if you're trying to unify gravity and quantum mechanics, gravity tells us the metric, the geometry, isn't fixed. It's dynamic, it's quantum, it might be fluctuating or uncertain.
Ah, the classic chicken and the egg problem.
Exactly. How can the particles, the eggs, exist if their very definition seems to require a metric? The chicken, but the metric itself is quantum and maybe not well defined.
So how does GU solve this?
GU's proposed solution is quite elegant. The spinors describing matter don't actually live on the base 4D space X4 with its potentially fuzzy metric.
They live somewhere else.
They live up in this larger 14-dimensional observer space, Y14. And the key is you can define spinors perfectly well in Y14 before you even choose a specific metric back down on X4.
Whoa. Okay, let me process that. Matter fundamentally exists in this higher observer space, independent of any specific way we might measure things in our everyday 4D world.
That's the core conceptual shift. The fundamental building blocks are defined relative to this space of possibilities, Y14.
That really changes the perspective on what matter is.
It does. And central to making this work is a specific geometric structure that's built over this Y14 space. It's a type of mathematical bundle, and it has a rather striking name.
Which is?
The chimeric bundle.
The chimeric bundle. Okay, these names are definitely memorable. What does this bundle do? What's its role?
So think of it like this. It combines different kinds of information available at each point in Y14. There's information about how the metric could change. Right at that point, you could think of that as sort of a vertical direction in the abstract space.
Changes in the metric itself.
Right. And then there's information related to directions or movement within the original 4D space, X4, a sort of horizontal aspect. The chimeric bundle weaves these together.
Vertical for metric changes, horizontal for space-time directions.
Roughly speaking. And importantly, this chimeric bundle comes equipped with its own natural way to measure distances within it. And the fundamental symmetries of the whole theory are deeply tied to this bundle, connected to mathematical groups like spin 77.
Okay, so recap. Start simple with 4D space, X4. Build this richer 14D space of all possible metrics, Y14. Construct a key structure over it called the chimeric bundle, which has its own geometry and symmetries. That's the setup.
That's the basic architecture, yes.
But how does all this abstract, high-dimensional math actually connect back to the concrete stuff we see? You know, the particles, the forces in our familiar 4D world.
Good question. The connection happens through something called observation maps.
Observation maps.
Yeah, these are essentially mathematical procedures like projections or specific ways of slicing through the higher dimensional space that translate information from Y14 back down to our 4D manifold X4.
So it's like Y14 holds the complete underlying reality.
Essentially.
And these observation maps are how we perceive a particular version or slice of it in our 4D experience.
That's a very good analogy. Y14 is like the full blueprint, and what we see in X4 is the result of looking at that blueprint through a specific observational process or lens.
And when you use these maps to bring things down from Y14 to X4, like those spinors we talked about.
Exactly. When you pull back the mathematical objects that represent fundamental things, like the spinors living on the chimeric bundle, down to the 4D manifold X4 using these observation maps, something really interesting happens. They naturally decompose or split up.
They break into pieces. And this is where the ingredients of our universe start to appear.
Precisely. This is where the source material gets really fascinating. It suggests that when this structure from Y14 is pulled back to X4, remember the vertical part, related to metric variations, that part seems to give rise to the internal symmetries of particles.
Wait, internal symmetries? You mean like electric charge? Or the color charge for quarks?
Exactly. Things like electric charge, color charge, weak isospin, the properties that distinguish different kinds of particles from each other beyond how they move in space-time.
Things like charge aren't just arbitrary labels. They're proposed to be geometric consequences of the different ways space-time could be measured up in Y14.
That's the incredibly profound geometric link being proposed here. It's suggesting that those internal quantum numbers arise from the geometry of the space of metrics.
Wow. And what about the other part, the horizontal part?
That part, related to directions in the original 4D space, seems to naturally give rise to the space-time properties.
Meaning how particles behave under rotations or boosts, like in special relativity. The Lorentz group stuff.
Exactly that. How the particles transform under changes in velocity or orientation in spacetime.
This is amazing. So this single geometric structure, when observed in our 4D world, naturally splits into two kinds of properties. The particle's identity, its internal charges, and how it moves and interacts with spacetime.
That's the claim. The geometry itself is purported to dictate both the internal quantum numbers and the spacetime behavior required for the fundamental matter particles, the fermions.
Okay, that's already huge. But then it gets even more specific, doesn't it? About the families of particles.
It really does. This is one of the most striking claims in the source material. Geometric unity doesn't just allow for the three generations of fermions we see.
Like the electron, muon, tau, and the different quark families.
Right. It claims to actually derive why there are three.
Derive the generations. Because in the standard model, we just Observe 3, we plug that number in. There's no fundamental reason given why it's 3 and not 1 or 5.
Exactly. It's an input parameter based on observation. GU suggests, however, that the three generations emerge completely naturally from a novel mathematical structure defined up on the Y14 space. It's related to how spinors behave in that higher dimension, involving something technically called a Dirac-Rita-Schwinger-like complex.
Okay, Dirac-Rita-Schwinger-like complex. Technical term, noted. But the key takeaway is that this specific mathematical structure within Y14 naturally produces how many distinct types of fermions?
It mathematically yields exactly three distinct types.
3. Matching observation.
Matching observation. The structure breaks down such that you get one type corresponding to the first generation, like the electron and its neutrino, coming from what you might loosely call a scalar spinor part.
Okay.
And then you get two more types. The second and third generations, muon, muon, neutrino, tau, tau, neutrino, coming from a vector spinor part, which itself splits into two pieces. And crucially, each of these three emergent types naturally carries the 16 internal degrees of freedom needed for a full standard model generation.
That's a potential game changer. The number of fundamental families isn't an assumption anymore, but an output of the geometry itself.
It's a massive aha moment if it holds up, definitely.
Okay, so that's matter. What about the forces, electromagnetism, the nuclear forces? Where did they come from in this picture?
They also arise naturally from the geometry of Y14. They're described as different components of a mathematical object called a connection.
A connect?
Yeah, it's a generalization of the idea of potential fields, like the electromagnetic potential. This connection is defined on a specific kind of bundle structure built over Y14.
So the forces are also geometric features woven into this higher dimensional observer space.
That's the idea. And deriving the equations that govern how these forces behave, the Yang-Mills equations, which generalize Maxwell's equations for electromagnetism.
Requires another new concept from GU.
Yes. Another key piece of mathematical technology introduced in GU is the Shiab operator.
The Shiab operator. Okay, what's its job? What problem does it solve?
Well, think about general relativity. Einstein gets his field equations for gravity by taking the Riemann curvature tensor, which describes space-time curvature in detail, and kind of simplifying it, contracting it down to get the Ricci tensor.
Right, a standard procedure in GR.
But that simple kind of contraction, if you tried to apply it directly to the curvatures related to forces in GU's framework, it wouldn't properly respect the symmetries of those force fields, what physicists call gauge symmetries.
Ah, so the standard contraction method breaks the force symmetries.
It doesn't play nicely with them in this unified context. The Shiab operator is designed as a more sophisticated, generalized way to contract or process this geometric curvature information, specifically constructed so that it does respect the gauge symmetries. It maintains gauge covariance.
I see. So it's a geometric tool tailored for this unified framework, one that handles both the gravity-like and force-like aspects correctly, respecting all the necessary symmetries.
That's the role it plays. And using the Shiab operator to process the curvature derived from that connection on Y14, you end up deriving the Yang-Mills equations, the equations that describe the dynamics of forces like electromagnetism and the strong and weak nuclear forces.
Okay, incredible. So we've got matter particles, we've got their division into 3 generations, and we've got the fundamental forces, all seemingly emerging from the geometry of Y14 and its associated structures. What about gravity itself? Einstein's equations. How does GR fit in?
The source material explains that the foundation of general relativity, the Einstein-Hilbert action, is also derived within this framework. It doesn't start the way GR usually does, by assuming a metric on our 4D spacetime x4 and calculating its curvature directly.
It starts higher up.
Yeah, it starts with a curvature of a special kind of connection defined on a structure that's sort of lifted even above Y14 using another construction with a memorable name.
Let me guess.
The Zorro construction.
There's a Zorro construction. Okay, I like it. Keeps things interesting.
Doesn't it? So you take the curvature of this structure derived via the Zorro construction, and then you process or compress that curvature using an operator that's related to the Shiab operator we just discussed.
Okay, so a similar symmetry-preserving compression technique.
Exactly. And when you take that result and pull it back down to our 4D space x4,
you get Einstein's theory.
You get the familiar Einstein tensor, which is the core mathematical object describing space-time curvature in general relativity. Essentially, you derive gravity.
That's really something. So gravity isn't fundamentally just about space-time bending in 4D. It's viewed as a consequence of processing curvature information from this higher dimensional observer's space setup in a way that's inherently unified with how the other forces are derived.
That's the picture. It provides a derivation of Einstein's equations from the geometry of Y14, crucially maintaining the gauge symmetries needed for the forces throughout the process.
Okay, that covers matter, forces, gravity. There's one big piece of the standard model puzzle left, the Higgs field.
Ah, yes, the Higgs, responsible for giving mass to most fundamental particles.
In the standard model, it feels a bit added on, a separate scalar field you have to include. How does GU handle the Higgs? Is it another separate piece?
This is another area where GU claims significant unification. According to the source material, the Higgs field is not added separately.
No. So where does it come from?
It emerges directly from a specific component of that gauge potential, the connection on Y14, the same object we talked about in relation to the forces.
Wait, the mathematical object describing the forces also contains the Higgs field within it.
Yes. When you take that gauge potential defined on Y14 and pull it back down to our 4D world X4 using those observation maps, it mathematically decomposes into different pieces, different types of fields on X4.
Okay.
One of those pieces transforms exactly like a scalar field, a field with just a magnitude at each point, no direction, like temperature.
Then that's the Higgs.
Specifically, the part of the pullback potential that looks like symmetric 2 tensors on X4. If you take the trace of that part, the specific mathematical operation averaging diagonal components, that resulting scalar component behaves precisely like the standard model Higgs field.
The trace of symmetric tensors derived from the Y14 gauge potential is the Higgs field. That's a very deep geometric identification.
It suggests a profound link. The trace part of this geometric object yields the spin-0 Higgs field, while the traceless part of the symmetric tensor is related to the spin-2 graviton, the particle of gravity.
Oh.
So in GU, they're not fundamentally separate fields added by hand. They're presented as different mathematical aspects of the same underlying geometric object defined up on Y14.
Linking the origin of mass, Higgs, and the mediator of gravity, graviton, to the same geometric parent. That's a huge step towards unification, conceptually.
It really is.
But the Higgs mechanism is famous for its potential energy shape, right? The Mexican hat potential. That specific shape is crucial for how particles actually acquire mass through symmetry breaking. Does GU predict that shape, or do you still have to put it in?
That's another critical point. The source indicates that this characteristic Mexican hat potential emerges naturally. You don't have to engineer it.
How?
Because the gauge potential in GU already contains the Higgs component. The standard self-interaction terms that naturally exist for gauge fields, part of the Yang-Mills structure, automatically generate a potential for that Higgs component, and it turns out to have precisely the required Mexican hat form, even with the right relative normalization.
So the very specific, seemingly fine-tuned shape of the Higgs potential just falls out of the standard gauge theory dynamics once you realize the Higgs is part of the gauge field in this framework.
That's the claim from the derivation. It's not an extra assumption.
Amazing. Okay, and connected to the Higgs giving mass, there's the Yukawa coupling.
Right, the specific interaction term that dictates how strongly each type of fermion, each quark and lepton interacts with the Higgs, which determines their individual masses.
In the standard model, these coupling strengths are just numbers we measure and plug in, lots of free parameters.
Yes, quite a few. But in GU, the claim is that the Yukawa coupling itself is also derived.
Derived how?
It comes from applying a very standard fundamental principle in physics called minimal coupling.
Minimal coupling. That's
Yeah.
just the basic way we already described how force fields interact with matter fields, right? Like how electrons interact with electromagnetism.
Exactly that principle.
Okay.
And remember, in GU, the gauge potential, the force field, already includes the Higgs component. So when you apply the principle of minimal coupling to the matter particles, represented by the direct operator acting on the spinors from the chimeric bundle, you're coupling them to the entire gauge potential.
Which includes the Higgs part.
Which includes the Higgs part.
Yeah.
So an interaction term automatically appears in the equations that represents the matter particles interacting with the Higgs component. And that term is the Yukawa coupling.
Wow. Okay, so the interaction that gives fundamental particles their unique masses isn't some new special kind of interaction you add on. It's just the standard minimal coupling interaction applied in this unified framework where the Higgs is already part of the force field.
That connection is derived directly from the geometry and the principle of minimal coupling. No new interaction types needed.
That ties things together incredibly neatly. What about the last piece of the puzzle, the CKM and PMNS matrices?
Ah, yes. The mixing matrices.
These describe how the different generations of quarks can morph into each other during weak interactions, and how neutrinos oscillate between their different types.
Electron, muon, tau, neutrinos.
Right. They capture the fact that the states that have definite mass aren't exactly the same as the states that participate in the weak force. There's a mismatch, a mixing.
And in the standard model, again, the parameters in these matrices are just measured values we put into the theory.
Yes, they are inputs determined by experiment. But in GU, the source material suggests that this mixing phenomenon also arises naturally from the structure.
How does that work?
It's proposed to come from the way the unified spinor field, representing all fermions up in Y14, decomposes when you pull it back down to our 4D space X4. The idea, roughly, is that there's some leftover gauge freedom.
Leftover gauge freedom, like some symmetry transformations still available?
Kind of residual geometric transformations possible in the internal space of the particles that don't perfectly align with the neat labels we give the three generations. This slight misalignment, this leftover freedom,
Causes the mixing. It means that when you look at the mathematical matrices that determine the masses of the quarks and leptons, they don't come out perfectly diagonal. A diagonal matrix would mean no mixing. Because they're non-diagonal, it implies that the mass states are mixtures of the weak interaction states.
And that non-diagonal nature, that mixing, is precisely what's described by the CKM matrix for quarks and the PMNS matrix for leptons.
Exactly. And the fact that these matrices have a key mathematical property called unitarity is also explained. It's simply a direct consequence of the underlying geometric gauge transformations being unitary themselves.
Okay, let's just take a breath here and look at the sheer scope of what geometric unity is attempting.
It's definitely ambitious.
Starting with just a basic 4D space, building this higher dimensional observer space, Y14, by considering all possible ways to measure distance, and then using specific geometric constructions like the chimeric bundle, operators like the Shiab operator, the Zorro construction, and these observation maps. The theory claims to derive gravity, Einstein's equations, all the fundamental forces, Yang mills, all the matter particles, fermions, their organization into precisely three generations, the mechanism by which they get mass, Higgs and Yukawa couplings emerging naturally, and even the way different generations mix together, CKM and PMNS matrices.
That is the breathtaking scope of the claim. It's an attempt to show that these fundamental pieces of physics, which, in the standard model plus GR, often feel somewhat separate or added ad hoc.
They aren't separate at all.
But instead, all emerge as different facets of one single coherent underlying geometric structure, rooted in this higher dimensional observer space.
It really feels like shifting from a picture where you assemble physics from a list of ingredients to one where you discover the fundamental reality is geometry, and all the physics we see is just the natural expression of that geometry.
It's like finding out the complex rules for how different chess pieces move, all derived from a single, deeper geometric principle on the board itself.
Yeah, that's a great analogy, replacing an empirical parameter-heavy description with, ideally, a deduction from first geometric principles.
That's the ultimate ambition, yes. A truly unified picture.
Now, of course, like any theory this ambitious, especially one aiming to rewrite fundamental physics, geometric unity is still very much a research program. It faces open questions, doesn't it?
Absolutely. It's not a completed edifice. The source material itself touches on several areas needing more work or clarification.
Such as?
Well, one intriguing possibility raised is the existence of decoupled sectors.
Decoupled sectors, meaning what?
Parts of the predicted particle spectrum coming from the geometry that don't correspond to the standard model particles we know, and crucially, don't interact with them through the known forces.
So hidden particles or forces predicted by the geometry?
Potentially. The question is, if they exist, how would we ever detect them? Maybe they only interact gravitationally. Perhaps high-energy gravitational effects could offer a window. It's an open area.
So the geometry might even predict more physics than we've currently observed.
That's a possibility. Another huge open question is the matter-antimatter asymmetry.
Why there's so much more matter than antimatter in the universe? A major puzzle.
Right. Does GU offer an explanation? Is antimatter perhaps hidden away in these hypothetical decoupled sectors? Or is the asymmetry just an initial condition, something put in at the beginning that the theory's structure doesn't itself explain? That's unclear.
And you mentioned numerical connections earlier.
Yes, the theory apparently generates some interesting numerical results that seem to align serendipitously with known physics, like the 16 internal dimensions per generation matching the standard model count, or perhaps relationships to structures explored in older attempts at grand unified theories.
But the question is, are these deep clues or just coincidences?
Exactly. How significant are these numerical alignments? Which ones might be genuine smoking guns, pointing to the theory being correct, and which could turn out to be mathematical red herrings? Sorting that out is vital.
Those are definitely big questions for ongoing research. So wrapping up our deep dive into geometric unity for now. We started by asking that fundamental question, what if the universe's basic ingredients aren't added, but derived solely from geometry?
And we saw how the theory proposes an answer. Starting with a simple 4D space, it constructs this much richer 14-dimensional geometric arena, the observer space Y14, by encompassing all possible ways to measure distance.
And then, through specific mathematical structures built on Y14, the chimeric bundle, the Shiab operator, and observation maps pulling information back down to our 4D world.
Geometric unity attempts to demonstrate how gravity, the forces, matter particles, their three generations, their masses via the Higgs and Yukawa couplings, and even their mixing patterns, all emerge naturally and coherently from that underlying geometry.
It's a vision aiming to replace a physics built by assembling parts with a physics derived wholesale from geometric principles.
A powerful top-down approach striving for that ultimate goal of unification that has driven physics for nearly a century.
Which leaves us, and you, with a final provocative thought to mull over. If this geometric picture, if geometric unity or something like it, is fundamentally on the right track,
Yeah.
does it imply that the physical reality we experience directly in our familiar four-dimensional spacetime is, in some deep sense, merely an observation, a projection?
A shadow, perhaps, of a much richer, more intricate geometric reality unfolding in higher dimensions. It certainly challenges our intuition about what's ultimately fundamental, the particles and forces we see, or the geometry from which they might arise.